Okay, hopefully you've had time to work through examples number 5 and number 6. So now it's time for me to work through it and let's see how you did. And if there's anything that you got wrong, make sure that you understand what your error was. And if you can't understand or find where your error was, make sure you email me and we'll sort it out. Okay, the first thing I noticed about number 5 is that my denominator is not in factored form. So I'm definitely going to want to get that denominator in factored form first, since many of the topics, or a lot of the information that I have to find requires that it be in factored form. So my denominator is a trinomial, so to factor it, it's going to factor into two binomials that when you multiply them out give you that trinomial. So the first term would be x and x to give me my x squared, and then I need factors of 2 that will add to 3, so not much choice there. It's going to have to be plus 2 and plus 1. So now let's go and start answering what we've been asked to find. So the domain, remember that I'm going to specifically look at the denominator and find out where I need to restrict my domain. So I want to set my denominator not equal to 0 and solve for x. So because my denominator has 2 factors, I'm going to have 2 restrictions. And those restrictions are x cannot be -2 and x cannot be -1. Now for the wholes, remember that what I want to look for now are common factors of my numerator and my denominator, and any common factors that they have are going to be wholes in my graph. So I do notice that I've got an x plus 2 in my denominator and an x plus 2 in my numerator. So this graph does have a hole in it. And the x value of the hole is going to be where I set that common factor equal to 0 and solve for x. So the x value of the hole is -2. And we'll want to find the y value for that hole because that will be an open point that we'll want to plot when we eventually get to graphing these. So before I find the y value of that hole, I'm going to rewrite my function one more time, completely simplified. So that means that I want to divide out what that common factor is and then work with the simplified form of that function. So I know that x plus 2 can divide out with x plus 2. So the simplified version of my function is x times x minus 3 all over x plus 1. So that's the version of the form of the function that I'm going to work with now for the y value of my hole and the vertical asymptote. So to find the y value of the hole, you're going to take the x value that we found, -2, and you're going to substitute it in for x into that simplified version of the function. So when we do that, we're going to get -2 times -2 minus 3 all over -2 plus 1. So it looks like on top in the parentheses, I'm going to get -5 times -2 is 10 over -1. So the y value for the hole is located at -10. And now when I go to find my vertical asymptote, the vertical asymptote is going to be when I take what's remaining in that denominator of my simplified version and set that equal to 0. So if I set x plus 1 equal to 0 and solve for x, that's where the vertical asymptote is located. All right, so now we want to move on to finding the horizontal asymptote. And we want to remember that for the horizontal asymptote, we want to find leading terms. And you can pull the leading terms of the numerator and the denominator either from the original function or from the simplified version of the function. So I'm going to use the simplified version of the function, this one here, because it just looks cleaner and I have fewer factors, so it's just a little bit easier to work with. So for the leading term of my numerator, remember I want to picture what this would look like multiplied out. So I've got two x's that would be multiplied together. So the leading term on top is x squared, and the leading term on the bottom is just a single x. So now you have to remember those three cases where I have more x's in the numerator. That for the horizontal asymptote, that means that there is none. So this means that my curve is going to increase or decrease without bound on the right or the left, and not have any leveling out where I need to draw in a horizontal asymptote. Moving on to the X-intercept. For the X-intercept, I want to remember that I want to set the function equal to 0 and solve for x. And once again, you can use the original function, but I would recommend using the simplified version of the function. If you do use the original function to find the x-intercepts, you need to make sure that you pay attention and not include an x-intercept that happens to be a restriction on the domain. So if I set the original function equal to 0, it's going to look like -2 is an x-intercept. But remember, -2 was a restriction. So just make sure that whatever you put on this line for your x-intercepts is not one of the restrictions that was on the domain. That would have to get thrown out. So to avoid that, if I use the simplified version of the function and set that equal to 0, then I don't have to worry about that. The intercepts that I get will be my intercepts. So remember last time I told you a little trick that anytime I'm setting a rational function equal to 0 and solving for x, that this denominator ends up getting divided out, and what I really end up having is just my numerator set equal to 0. Because when you multiply this side, of course, by x plus 1, that's still going to remain 0. So again, that shortcut of when I'm setting a rational function equal to 0 for my intercepts, it really is just the numerator that is set equal to 0, and I solve for x. So I notice, since this is already in factored form, that I'm going to have two x-intercepts, one for each one of those factors. So this is x equal to 0, and my other factor is x equal to 3. So as ordered pairs, that would be x-intercepts 0, 0, and 3, 0. Now for the y-intercept, when I go to find the y-intercept, that one's the easy one because I just want to let x equal 0 everywhere in the function. And once again, you can use the original or you can use the simplified version of the function. So again, the simplified version is easier to manipulate and to work with, so that's the one I'm going to use. So everywhere I see an x, I'm going to replace it with 0. So I'd get 0 times 0 minus 3 over 0 plus 1. And of course, 0 times anything is just 0, and 0 divided by anything except for 0 is 0. So my y-intercept is located at 0. I'm sorry, I don't know where the 1 came from. At 0, 0. I was thinking about that 1 there. But we got 0 when we plugged in 0, so my y-intercept is 0, 0. So how'd you do? You were going to work on this problem before you looked at the video, so check yourself to see if you got them all right, or if you made an error, that you know what your error is. And if you don't know what your error is, email me so we can sort that out. Now, I've got one more example of these that I want to do. So if you want to, you can pause the video and make sure you run through that problem by yourself first so that you can check yourself to see how you did. Especially if you learned something from this example, then go through and try this problem first before you watch me do it. Okay, first thing I notice about number 6 is that it is not in factored form. So I am going to have to factor this before I can start. So in my numerator, I can factor out a greatest common factor of 4. So if I divide out a 4 from each of those terms, I get x plus 2. And in the denominator, I've got the difference of two squares. So it's going to factor into x plus 2 and x minus 2. So now when I go to the domain, I'm going to look for any restrictions based on the denominator of the function. So I'm looking here for the domain, and I notice that x cannot be -2, x cannot be 2, since those are the two values that would give me 0 for either one of those factors. Now when I move on to the whole, I'm looking for a common factor. So just remind yourself what you look for to find that item. And for wholes, it's common factors from the numerator to the denominator. And I can see right now that I've got an x plus 2 in both the numerator and the denominator. So if I set that common factor equal to 0 and solve for x, I know that the x value of that open point is going to be at -2. Now remember that before I go to find the y value for that whole, I want to simplify my function. So I'm going to divide out this common x plus 2 in my numerator and denominator, which will leave me a simplified version of my function, 4 over x minus 2. And now I can identify what the y value of that whole is. So now I'm going to plug in that -2 into that simplified version to get the y value. So 4 over -2 minus 2 would be 4 over -4. So the y value for that whole is -1. Now I move to the vertical asymptote. And for the vertical asymptote, I want to look at the denominator of that simplified version and identify what I get when I set that denominator equal to 0. And if I do that, I'm going to get x equal to 2. So that's where the vertical asymptote exists. And now I'm ready for the horizontal asymptote. For the horizontal asymptote, I want to compare my leading term on top to my leading term on the bottom. And my leading terms are going to be, for the numerator is 4, and for my denominator it's x. So now I go back and think about those three cases. When I have more x's in the denominator than I do in the numerator, then the horizontal asymptote is located at y equal to 0. Now moving to the x-intercept. For the x-intercept, I want to set the function equal to 0. And again, I'll use the simplified version of my function to do that. And remember that since this is rational, try to remember that shortcut that says I really just need to set the numerator equal to 0. Now, when I set that numerator equal to 0, I get a statement that doesn't make any sense. I get a statement that says 4 equals 0, and clearly that's not true. So if I can't find what I'm looking for, it means that what I'm looking for does not exist. So I do not have any x-intercepts on the graph of this function. And finally, the last one that we need to find is the y-intercept. And for my y-intercept, we're going to let x equal 0. And again, if I use the simplified version of my function, I'm going to plug in 0 for x. So again, I'm using that simplified version. Once I find that simplified version of my function, that's literally the part of the function that I'm going to refer back to for everything else. So after I've found the x value of that whole, to find the y value, the asymptotes, and the intercepts, I'm just going to keep referring to that simplified version of the function. So I get 4 over -2, which is -2, so my y-intercept is located at 0, -2. So hopefully that time you did a lot better on your own, but if there is something that you're still having trouble understanding where to find that information, or if you see something that I did that you don't quite understand, just email me and we will get to the bottom of it so that you understand the material. So next up on the agenda are graphing these buggers. So we'll still have to pull all of this information out from the function, but then we're going to take all this information and put it together in a graph of the function. But now you want to go in and make sure that you do your homework for 3.5 Rational Functions Part 1, where you're just going to practice pulling all of this information out first.